I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to derive the wave equations for transverse waves as well as longitudinal waves. So if you see in this module, harmonic oscillations and waves in one dimension, we have already discussed the oscillations part and we have started with waves in our previous lecture, and we have discussed in deep about transverse and longitudinal waves. All the basic concepts and the definitions we have already discussed in our previous lectures, and today we will be using those concepts to derive the wave equations. Those of you who have not seen this video, I request you to go through the videos on transverse and longitudinal waves so that it will be very easy for you to understand the wave equations. Now let us see how we are going to do this lecture today. So first we are going to derive the equation for a transverse wave on a string, and then we'll derive the expression for the velocity of a transverse wave. And the same thing will repeat for longitudinal wave. First we'll derive the equation for longitudinal wave and then get the expression for the velocity of a longitudinal wave. Now let us quickly see what we have seen yesterday in the general wave equation. Before going into specific for transverse waves and longitudinal waves, we will quickly recollect what is the general wave equation for a string. Means what we have considered here is a string which is tied at both the ends. Means this is under tension. So when we just display, pluck it and leave it, so the wire or the string starts vibrating and there will be waves. So what is the general expression for the displacement of the wave? So we know that y is given by a cos kx minus omega t, where k is the wave vector given by 2 pi by lambda and omega is the angular frequency given by 2 pi by t. So now how we are deriving the equation? First we have taken the derivative with respect to x, because here there are two variables x and t. First we are going to differentiate it with respect to x. So we are taking the partial derivative. Dou y by dou x is minus ka sine kx minus omega t. Then take the second derivative. Dou square y by dou x square will be minus k square a cos kx minus omega t. So this is what we have done for x. We are differentiating with respect to x and keeping our time constant. Now let us take the derivative with respect to t. So dou y by dou t will be omega a sine kx minus omega t. Here kx, here this remains constant. So what we have here is omega a sine kx minus omega t. Taking the second derivative, we get dou square y by dou t square, that will be minus omega square a cos kx minus omega t. Let it be equation 2. Now we are going to compare these two expressions, get the value of a cos omega t from here and substitute in this equation. So what we get is dou square y by dou x square is equal to 1 by v square dou square y by dou t square. So this is the general expression for any wave. This is the general expression, where v here represents the velocity of the wave. V represents the velocity of wave. Now let us go to derive the expression for transverse wave on a string. So we will see the expression for a transverse wave. So when we pluck a string under tension, a transverse wave moves in the positive direction as shown in the figure. We have already discussed what a transverse wave is. Suppose you have a string here and if you just pluck it and leave it, all the particles of the string will vibrate perpendicular to the direction of motion of the wave. So you will have a wave which is moving in the forward direction, in the positive direction. Now let us consider a small element delta x. We'll consider a small element. So you can see the line, the string here, we are considering only a small element. We'll denote it by AB. AB is the string, the element, small element of the string under consideration. Okay, so the element is delta x. The mass element is small but is enlarged in the figure to make it visible. If you think that this is the length, no, it is very small, but for us to understand, it is enlarged here. Means if I take a string like this, I'll take a very small element like this, delta x, which is now enlarged for us to understand the tension that is acting on the string. So AB is a very small element. Now the small mass element oscillates perpendicular to the wave motion. We are seeing transverse wave. So how they are oscillating? It oscillates perpendicular to the wave motion, and as a result of the restoring force provided by the string, it does not move in the x direction. It does not move forward. It only vibrates about the mean position, and the restoring force always tries to bring it back to the equilibrium position. So what we are trying to understand here is the small element which is under consideration is vibrating about its mean position or the equilibrium position perpendicular to the direction of motion of the wave, and hence it does not move. The string is not displaced, only the wave is propagating in the forward direction. Now let us see the coordinates of the element AB. We have considered element AB, a very small element AB. Now let us write the coordinates of A as xy. So the coordinates of A are x, y. The x coordinate is x, y coordinate is y, xy. And the coordinates of B are x plus delta x and y plus delta y. So the coordinates of this point B are x plus delta x and y plus delta y. And let the displacements be small and the tension remain unaltered when the string vibrates in the xy plane. So how is the string vibrating? Up and down in the xy plane. Now let us draw two tangents, T1 and T2 at the ends of the string. So what is a tangent? A line drawn normal at that point. So T1 is the tangent at this point and T2 is the tangent at this point. So a line which is drawn tangential at that particular point, we call them as tangents. And they make angles theta 1 and theta 2 with the x-axis. So this will make, if this is the x-axis, so this will be theta 2 and this will be theta 1. So T1 and T2 represent the tensions at the ends of the string. Now these tensions T1 and T2 can be resolved into two components. So T1 can be resolved into T1x along the negative x-axis. So I can write, if this is T1, I am going to resolve it into T1x and T1y. So this is the negative. If I am taking this point as origin, so on to this side is negative along the negative x-axis, and downward also we consider it as negative. I can say this will be in the third quadrant. So T1 can be resolved into two components, one along the x-axis and one along the y-axis. Here they are along the negative x-axis. So this T here is T1x and this is T1y. Now the same way, T2 can also be resolved into two components. So this is our T2 which is drawn at the end of the string. This also can be resolved into two components. Can say this will be T2x, which is nothing but T, and this is T21. So we are resolving it into two components. And if you see here, this x components, T1x and T2x. If I say here, this is T1x. T1x and T2x are equal in magnitude, but they are opposite in direction. If you see, the direction of T2x is along the positive x-axis and the direction of T1x is along the negative x-axis. But if you see, the magnitudes are the same. So they cancel each other. So what we are trying to understand here is, what is the tension acting on the string? First, we have considered T1 and T2. We have resolved them into components, but we find that the x components are getting cancelled out because they are equal and opposite. So what will be the net tension acting on the string, or the resultant tension will be only due to the y components because the x component got cancelled out. So we don't have this T and T, these two are cancelling out. So what is the resultant here is T1y acting in the downward direction at A and T2y acting in the upward direction at B. So the resultant Fy is equal to T2y plus T1y. So it is not equal. The force is due to, I may not write it is equal, but it is due to the tensions T2y and T1y, the resultant of these two tensions. So let us consider this as equation 1. Now how do we write T2y? So T2y is given by T into dou y by dou x at x plus delta x. So T2y at the point B. We have already considered the coordinates here, x plus delta x and y plus delta y. So T dou y by dou x at x plus delta x, and T1y, the coordinates are xy. So T1y is equal to minus T dou y by dou x at x. Why minus T? Because it is in the downward direction. So the positive y-axis in the upward direction we consider, and in the downward direction we consider it as negative. So T2y is positive, whereas T1y is negative. So now we are going to substitute these two, the second equation in 1. So we get the force due to these two tensions, T into dou y by dx at x plus delta x minus T dou y by dou x at x. So now if you see Newton's second law. So what does Newton's second law tell us? F is equal to ma. Force is equal to mass into acceleration. And acceleration is nothing but rate of change of velocity. And we are writing it by m into d square x by dt square. F is equal to m into d square x by dt square. And now here, small m here denotes the length of the string, mass of the string, sorry. M denotes the mass of the string. The string, if you consider the total mass of the string. But here we are only considering a small element delta x. Delta x is the small element of mass under consideration. So now what will be the mass of this element we have to consider here? So for that what we do is we calculate first the mass per unit length. Mass per unit length. So what is mass per unit length? Given by m by L. If L is the total length of the string and m is the total mass, so the mass per unit length of the string is given by m by L, which is denoted by mu. So mu gives the mass per unit length of the string. Now what will be the mass for delta x element? So that will be mu into delta x. So here for m, we substitute mu into delta x, d square x by dt. So here we are writing it directly. Fy is equal to m into d square y by dt square. We are not writing in terms of x because we are taking the y component. So I have given a generalized definition or the formula here. And what we are applying now is for the y because the tension is now along the y-axis. So this is m d square y by dt square. And m is nothing but mu into delta x d square y by dt square. Let this be equation number 4. Now we are going to equate equations 3 and 4. So what is our equation 3? This is our equation 3. Fy is equal to t dou y by dou x at x plus delta x minus t dou y by dou x at x. So we are going to substitute or we are going to equate, compare these two expressions. So the left hand side is the same, Fy. On for both the equations, the left hand side is Fy. So we can equate the right hand sides. So when we equate, what do we get? T dou y by dou x at x plus delta x minus t dou y by dou x at x. This is what we have from equation 3. So this can be equated to the right hand side of equation 4. So what is there in equation 4? Mu delta x dou square y by dou t square. So we are now equating these two equations. So the right hand sides are equated. Now if I have to rearrange the terms and write, I can bring delta x onto this side. So t dou y by dou x at x plus delta x minus t dou y by dou x at x upon delta x will give us mu dou square y by dou t square. So tension divided by the length of the element. Let this be equation 5. Now we are going to simplify the expression. We have t dou y by dou x at x plus delta x minus t dou y by dou x at x. So when we expand this term, what do we get? T dou square y by dou x square, because it is dou by dou x of dou y by dou x plus dou y by dou x. So we have two terms now. On expanding this, we get t dou square y by dou x square plus t dou y by dou x minus the second term. What is the second term? Minus t dou y by dou x upon delta x. Now here you have plus dou y by dou x into t, and this is minus dou y by dou x into t. These two will get cancelled. So what we are left with is t dou square y by dou x square upon delta x. So on simplifying this left hand side, what we are left with only t dou square y by dou x square. And here what we are doing is we are simply neglecting the value of delta x, or if delta x tends to 0. If delta x tends to 0, then we are simply writing it as t dou square y by dou x square. Let this be equation 6. Now if you compare equation 4 and equation 6, we are going to compare 5 and 6. So what is our equation 5? T dou y by dou x at x plus delta x minus t dou y by dou x at x upon delta x is equal to mu dou square y by dou t square. Now this whole thing, instead of this, we can write t dou square y by dou x square. So we are going to substitute this here. So what we are doing here is substitution. I'll write one more step. We have t dou square y by dou x square This is from equation 6 is equal to, from equation 5 what we have, mu dou square y by dou t square. So on comparing the equations, we are getting t dou square y by dou x square is equal to mu dou square y by dou t square. Now I can rearrange the terms because I want to write what is dou square y by dou x square. So on transposing, t comes to the denominator. So mu by t dou square y by dou t square. So dou square y by dou x square is equal to mu by t dou square y by dou t square. So this is the expression we get for a transverse wave. So the expression for a transverse wave is given by dou square y by dou x square is equal to mu by t dou square y by dou t square. What is mu here? Mu is the mass per unit length and capital T is the tension in the string. Now let us get the expression for velocity of a transverse wave. What will be the velocity with which a transverse wave moves? So for this, we need to compare the two equations, the transverse wave equation with the general wave equation. So what is the general wave equation we have? Dou square y by dou x square is equal to 1 by v square dou square y by dou t square. Here x and t, what they denote is y is a function of x and t because it varies with time. The displacement varies with time. So we are having two variables. That is why I'm reading it as dou square y by dou x square is equal to 1 by v square dou square y by dou t square. So what we are getting for a transverse wave is dou square y by dou x square is equal to mu by t dou square y by dou t square. It is understood here. This is also a function of x and t, displacement and time. Okay. So when you compare again, the left hand side is the same. So we try to compare the right hand side. So comparing the transverse wave equation with the general wave equation. So what we are going to get, 1 by v square is equal to mu by t. So what you have here is 1 by v square and what you have here is mu by t. The rest of the terms remain the same. Dou square y by dou x square, dou square y by dou x square, dou square y by dou t square and dou square y by dou t square. So what we are going to do is now compare the two expressions. You get 1 by v square is equal to mu by t. So we want to get the velocity. So I can write it as v square is equal to t by mu. And taking the square root on both sides, we get v is equal to under root t by mu. So the expression for velocity is given by v is equal to under root t by mu. So v is the velocity here. V represents the velocity. T is the tension. And mu is mass per unit length. Mu is mass per unit length. So we have the transverse wave equation also and we get the expression for velocity also. Now the speed of waves in a stretched string depends upon the tension T as well as the mass per unit length of the string. And how do we explain it? Is more the string is stretched, the faster the waves travel in it. That is the meaning, because we have V is equal to T under root T by mu. So I can say V is directly proportional to root T. So as the tension increases, means more the stretch in the string, more the velocity. So as the string is stretched more, the waves will travel faster in it. And the formula is V is equal to under root T by mu. It also, of course, depends upon the mass per unit length. if the mass increases, because it is inversely proportional, 1 upon under root mu. So if mu is less, the velocity will be more. So the faster it moves, lesser the mass per unit length, faster the wave moves or greater the velocity. Mu here represents m by L. This we have already seen. Mu is the mass per unit length, where capital M represents the total mass of the string and capital L here represents the total length of the string. So mu is equal to capital M by L. Now, before we go to derive the longitudinal wave equation, it is very important to recollect some formulae related to longitudinal waves. So, the first one we are going to see is stress. Stress is given by force upon area. We'll be using all these formulae again and again. So, let us first try to understand this and then we'll go and do the derivation. So, for this, I'll just give you a simple example. We take a string to which a mass m is attached. This is suspended from a rigid support. Now, let L be the length of the string. Now, because of this mass, there may be some elongation in the wire. So, let the elongation be small l. So, I can write after elongation. This is before elongation. And after elongation, let this be the small elongation in the wire due to the mass m. So, this is our original length L and this is the extension or the elongation L. Now, if we have to calculate the stress that is acting on the wire, so it is given by force upon area. So, what is the force here? It is due to the mass. So, here F is given by mg. And the area will be the area of cross section of the wire, which will be pi r square. Because the string we consider is circular in cross section. So, stress is given by mg upon pi r square. Now, coming to Young's modulus. So, what is Young's modulus? This comes from the Hooke's law we have seen. So, Young's modulus, what it says is the ratio of stress to strain is a constant. So, Young's modulus is equal to longitudinal stress upon longitudinal strain. Longitudinal, why we are considering? We are only considering the elongation lengthwise. So, what is the longitudinal stress and what is the longitudinal strain? So, in this case, if I am talking about stress, it is longitudinal stress. Stress is equal to force upon area is a general formula. But here, when we are talking about the string which is stretched lengthwise, the stress acting on it is longitudinal stress and it is given by force upon area, that is mg upon pi r square. So, the Young's modulus is given by longitudinal stress upon longitudinal strain. And how do we get the longitudinal strain? It is always the change in length upon original length. Change in length upon original length. So, what is the change in length given by small l? What is the original length? Capital L. So, whenever we have to calculate the strain, longitudinal strain, we always consider the change in length upon original length. Then, what is density? Density is mass per unit volume. So, when I have to calculate the density of the wire, it will be the total mass of the wire divided by volume. But from here, if I have to get the volume will be equal to, I can write, if I have to write volume will be equal to mass upon density. Because density is equal to mass per unit volume. If I have to find the volume, volume will be mass upon density. So if I'm given the total mass and the density, I can find the volume. Now, another formula to calculate volume is area into length. So whenever we are talking about a block, so volume of a block, if I consider this as a three-dimensional block or a cube, okay, cubical, it is cubical. So volume will be area into length, L into B into H we can consider. So area into length. So we always consider for volume, area into length. So with these formulae in mind, we will go to derive the expression for longitudinal waves. So first of all, we'll recollect what a longitudinal wave is. We have already discussed in the last class. We said, suppose we take a wire which is fixed at both the ends, means there is tension in the string. We are stretching it tight and holding it. So there is tension in the string. When you pluck it and leave it, if the particles of the string vibrate like this, how they are moving or how they are vibrating? They are vibrating parallel to the direction of propagation of the wave. So if this is the direction of the wave, so this is how the particles are vibrating. Again, here what we need to understand is the particles are not moving from their place. They are not displaced. Only thing is they are vibrating about the mean position. But at any point of time, you see, because of this movement, there may be some displacement in that cross section. That is what we are going to consider here. So now we are going to take a long uniform rod, means of uniform area of cross section. The cross section should be uniform throughout. So this is the long rod we have considered, whose cross section is uniform. And before the wave moves through it, we are considering a section which is delta x. A small section we will focus on at x, a small element delta x. That is before the wave moves. Now, when a wave moves through this rod, that is in the presence of the wave, what happens is this layer which is here is getting displaced. So when the particles vibrate like this, what happens? The layer is getting displaced. So it is displaced through delta n, I can say. So wave exists all through the rod, but what we are doing, we just consider a small segment delta x. For our study, we are considering a small segment delta x. And in the presence of the wave, this segment delta x shifts and stretches by a longitudinal displacement delta n. So what is delta n here? Delta n represents the longitudinal displacement. So we know delta x we have considered, and because of the wave, there is a displacement which is denoted by delta n. So now our slide shifted due to the cumulative strains and also stretched by delta n. So because of that, there are the forces that are acting on the slice. So let me show you how the forces are acting. So we have considered a uniform rod, and here we have taken a small element delta x, and because of the wave passing through it, there is a small displacement delta n. So now what we are considering here is delta x plus delta n. Delta n is a small displacement. Now because of this, there are forces F1 at the front of the slide and F2 at the back of the slice. So here you may have F1. I'm considering only the slice delta x. So here again there will be a force F2. So these will be the forces that are acting. One on the front slide. This is, I consider it as the front slice, and F2 at the back slice. So now what is the strain on the slice? So we have already seen the formula for strain. The general formula for strain is change in length upon original length. Strain is always given by change in length upon original length. So what is the change or the displacement we are seeing here is delta n. So it is delta n upon delta x. So the average strain is given by delta n upon delta x. Now what is the stress? What is the stress? We also have seen the formula for stress. Stress is equal to force upon area. Stress is equal to force upon area. Now we want to write the stress. And what is longitudinal stress given by? Longitudinal stress upon longitudinal strain gives us y. That is the Young's modulus. Stress is now given by y into longitudinal strain. So we are going to use this formula. Longitudinal stress is equal to y into longitudinal strain. Y is the Young's modulus, which is a constant for a given material. So what we are doing now is to write stress. We have taken y multiplied by the strain, y into strain. So delta eta by delta x is giving us the strain. The average strain is given by delta eta by delta x. So y into delta eta by delta x is giving us the average stress. Now let us consider the stress at point x first. So at the initial point, what is the stress? So the stress is given by y into dou eta by dou x. So this is the strain at any point x. We consider dou eta by dou x. So y into strain is giving us the stress. So why we are taking partial derivative here? Because time, it is also time dependent. So we are talking only with respect to the displacement here. So we are talking in terms of partial derivative. Okay, and not d eta by dx. Now what is the stress at the point x plus delta x? So what is the stress at delta x plus delta x? We have stress at delta x plus delta x is given by stress at x plus dou by dou x of stress into dx. So first let us write the stress at x. Stress at x we have already represented by y dou eta by dou x. So y dou eta by dou x here represents the stress at x. And what is dou by dou x of a stress? So this will be given by dou by dou x of y into dou eta by dou x into delta x is anyway there. So we are going to substitute the same thing. For y we are substituting y dou eta by dou x into delta x. So if you write this, what will you get? Y into dou eta by dou x plus y dou by dou x of dou eta by dou x, we get the dou square eta by dou x square into delta x. This is what we get. So now we have the stress at each end. And how do we get the force at x? So force is now given by, because we have stress is equal to force upon area. Stress is force upon area. So force will be equal to stress into area. Area here is the cross-sectional area. So what is the stress we got at x? Y into dou eta by dou x. And the area, the cross-sectional area is represented by alpha. Alpha here represents the cross-sectional area. So force is given by stress into area. So this is the stress and this is the cross-sectional area. This is F1. Then what is F2? We are talking about two forces on either ends of the slice. So F1 and F2 will be at x plus delta x, the other end. So at x plus delta x, what it will be? Alpha y dou eta by dou x. So this is the area multiplied by the stress at x, and alpha, this is the area multiplied by the stress at x plus delta x. So what we have got at x plus delta x is alpha y dou square eta by dou x square into delta x. So what will be the net force or the resultant force? So the net force is given by F2 minus F1, because when we have taken the slice here, if this is x and this is after a distance delta x, this is x plus delta x. If the force acting on the slice is F1 and on the slice is F2, so the resultant force will be F2 minus F1. F1 is acting in the positive direction and F1 is in the negative direction. So the resultant is given by F2 minus F1. So what is F2 minus F1? We have F2 as alpha y dou eta by dou x plus alpha y dou square eta by dou x square into delta x minus alpha y dou eta by dou x. So these two terms will get cancelled. What we are left with is only alpha y dou square eta by dou x square into delta x. And we also know from our Newton's second law, F, the resultant force, is given by ma, mass into acceleration. So what is acceleration given by dou square eta by dou t square? This is giving us the acceleration. And how do we get the mass? Mass of the element that we are considering. So we know mass density is equal to, you can write here, density is equal to mass by volume, and volume is also given by area into length. Area of the slice that we are considering multiplied by the length gives the volume of that slice. So density is equal to mass upon area into length. So if I want mass, I can also write density multiplied by area multiplied by length. So this is the formula we are writing here. How we are getting it? From our basic formula, density is equal to mass by volume. So mass is equal to density into area into length. So here, let the density be represented by rho. Rho denotes the density. And the area of cross-section or the cross-sectional area is represented by alpha. And the length we are considering here is delta x. So delta x here is the length. So how do we get the mass now? Density multiplied by area multiplied by length. So F2 minus F1 is equal to m into A. For m, we are going to substitute rho alpha delta x. So alpha y dou square eta by dou x square into delta x should be equal to, this is mass and this is acceleration. So we are going to equate them. So now when we can simplify them, what we have on the right hand side, alpha y dou square eta by dou x square into delta x will be equal to rho alpha delta x into dou square eta by dou t square. What are the terms that are going to get cancelled? Alpha gets cancelled, delta x gets cancelled, and we have dou square eta by dou x square is equal to rho. If I bring y onto the side, it goes to the denominator, rho by y, dou square eta by dou t square. So this is the equation we get for longitudinal waves. So we are cancelling the terms on either side, and what we are left with, dou square eta by dou x square is equal to rho by y dou square eta by dou t square. Now what we are going to do is, we are going to compare it with our general expression for a longitudinal wave. So what will be the expression? Dou square eta by dou x square will be equal to 1 by v square. We have already derived the general expression. Now 1 by v square dou square eta by dou t square. So let us compare these two equations now. What is there on the right hand side is the same. So let us compare the left hand side. So rho by y dou square eta by dou t square will be equal to 1 by v square dou square eta by dou t square. So this gets cancelled. We have rho by y is equal to 1 by v square. This implies v square is equal to y by rho. If I want to get v will be equal to under root y by rho. Y represents the Young's modulus and rho is the density. So this is the expression for the velocity of a wave, a longitudinal wave. So let us try to understand both now, how we can relate the terms and understand. In a stretched string, when there are transverse oscillations, means when we are talking about a wave, transverse wave traveling, the particles vibrate perpendicular to the direction of motion. Then dou square y by dou t square will be equal to t by mu dou square y by dou x square. And v is given by under root t by mu, where t is the tension and mu is the mass per unit length. No? So this is the expression in case of transverse. So how do we write for longitudinal waves? Dou square eta by dou t square is equal to y by rho dou square eta by dou x square. You may ask, before we have written for dou square eta by dou x square is equal to rho by y dou square eta by dou t square. Here we are writing it the other way. Doesn't matter. Well, for comparison's sake, what we are doing, dou square eta by dou t square is equal to y by rho dou square eta by dou x square. Now, if you see here, y is what? Y is the transverse displacement because the particles are vibrating perpendicular. And eta here represents the longitudinal displacement where the particles vibrate parallel to the direction of motion. So here we are talking in terms of y, the transverse displacement, and eta here denotes the longitudinal displacement. So when you compare, what we are getting, v is equal to y by rho. So here it is under root t by mu, tension upon mass per unit length. Here it is Young's modulus upon density under root. So thank you and see you again in the next lecture. For more reference, you can refer to books by Engineering Physics by Harbola and Vijay Krishna, and also Engineering Physics by Palaniswamy. Thank you and see you.
Like, share and subscribe. Hit the bell icon for more updates.